Welcome back to TalkTensors. I'm excited for today's deep dive. We're going to be looking at efficient neural clause selection reinforcement.
Yeah.
So, right off the bat, this paper tackles like a really core problem in automated theorem proving.
Yeah.
You know how to get computers to think logically, to actually prove mathematical statements.
Yeah, absolutely. And you hit the nail on the head there. It's all about, this crucial bottleneck in ATP. It's that clause selection step. So think of it like, I don't know, you've got a detective, they're working a case, they've got a ton of clues, right? Which ones did they focus on first?
Yeah.
It's the same thing in theorem proving. Picking the right piece of information, the right clause can make or break the whole process. And what these researchers did is they said, hey, can we use reinforcement learning, like neural networks and stuff, to automate this and make it way better?
Exactly. I mean, for ages, it's been all about these handcrafted rules.
Mm-hmm.
Human experts, they spend, years coming up with these clever ways to pick clauses. But here, they're like, let's just let the prover learn for itself. Learn from its mistakes, figure out what works. Kind of like, a self-driving car, right?
Yeah.
Instead of just programming all the rules of the road, let it drive around and figure it out.
That's a great analogy. And the cool thing is they actually built this. They put it into Vampire, which for folks who don't know is like one of the leading theorem provers out there. Really powerful, really fast. And their key innovation was designing a neural network that could handle the complexity of logic, but do it quickly so it doesn't slow Vampire down.
Yeah,
Yeah.
Speed is key, right?
Yeah.
And the results, man, they're pretty impressive. So they tested it on this benchmark, the TPTP, basically the gold standard test suite for theorem provers. And their neurally guided system, boom, 20% improvement over Vampire's default strategy. And they did it within a practical time limit. But what really blew me away, they solved over 100 problems that had never been solved before by any system. That's huge. I mean, that's not just an incremental improvement. That's pushing the boundaries of what we thought was possible.
Yeah, no, that's a major achievement. Like solving those unsolved problems, that tells you there's something really new happening here. Not just refining existing approaches, but potentially finding completely new ways to crack these tough proofs. So to understand how they did this, let's actually take a closer look at the paper. It's very well structured. They lay out their approach really nicely.
Yeah, and they start by setting the stage, right? Explaining why this problem matters. I mean, reinforcement learning, look what it's done in games and all sorts of decision-making tasks. It's revolutionized those fields. And they point out that, a lot of past work in theorem proving with machine learning, it used supervised learning. That needs lots of labeled data, right? And it often focused on very specific types of problems. So their goal here, they wanted to explore if reinforcement learning could discover these more general, unbiased strategies that could work across a much wider range of problems. And they do it by letting the prover learn directly from its own experience in trying to find proofs.
Right. And their goal, explicitly stated, was to use this specific type of reinforcement learning called policy gradient. And the idea is to train a neural network to make those crucial clause selection decisions right inside Vampire. They also stressed how important it is for this neural network to be efficient. You don't want it bogging down the whole system. And they introduced this interesting learning operator, their own way of updating the neural network based on successful proofs. Also, one really key decision, they focused on selecting one clause at a time from a single queue. They didn't try to model the entire state of the proof process, which can get really complex.
Yeah, that stateless approach is a big choice. Maybe for general theorem proving, where things are messy, it's just more effective to pick the best looking clause right now than to get bogged down in all the history of what happened before.
Mm-hmm.
But let's take a step back for a second. The background section of the paper is great for context. They explain this idea of saturation-based theorem proving. That's how Vampire works, right?
Yep. You take the thing you want to prove, you assume it's false, and then you try to derive a contradiction. And that contradiction, in logic terms, is the empty clause. Basically, it's like saying something and its opposite are true at the same time, which is impossible.
And to do this, they use this given clause algorithm. So they've got two sets of statements. The active set, which is the stuff they've already looked at, and the passive set, which is all the statements waiting to be processed. And the main loop is pick a clause from the passive set, move it to the active set, and then use it to infer new logical statements.
Exactly. And that brings us right back to the central problem. Which clause should the prover pick from that passive set? And the paper points out, the ideal strategy, picking the clause that'll lead you straight to the proof, well, You can't know that in advance. So provers rely on heuristics, which are like, rules of thumb. They might prioritize older clauses, thinking maybe they're more important because they've been around longer. Or they might prefer shorter, simpler clauses. And often these heuristics are combined with some higher level strategy that decides which rule to use when.
Right, makes sense. So then they go on to give a really nice explanation of reinforcement learning. For those not familiar, it's a way for an agent, in this case our neural network, to learn how to make decisions. And it learns by interacting with an environment, and it gets rewards or penalties for its actions. The goal is for the agent to figure out the best way to act, a policy that maximizes its reward in the long run. And the paper specifically mentions Markov decision processes, which is a formal way to model these sequential decision-making problems.
Okay, so now we can connect this to clause selection. What the researchers did is they said, hey, this whole clause selection process, we can think of it as an RL agent. The environment is the state of the theorem prover, and the actions are the choices of which clause to pick next. The final reward, the big payoff, is deriving that empty clause, which means you've got a proof. And their goal then was to design a better agent, their neural network, that could learn to pick clauses more effectively than these hand-designed heuristics.
Yeah, and it goes back to that state thing, right?
Yeah.
They noticed that even in these really sophisticated provers, the actual decision of which clause to pick often doesn't depend that much on the whole history of the proof. For efficiency, they tend to just grab the best-looking clause at that moment based on some evaluation. So that's why they went with this stateless approach. The neural network is mostly focused on the clauses available right now in the passive set, not the entire proof history. And the actions are simply picking one of those clauses.
Now, the reward in RL is super important for guiding the learning process. But just giving a reward when you finally hit that empty clause, especially in a stateless setting, well, that doesn't give you much feedback to work with. So the authors came up with this clever idea. They call it a retrospective reward. After a proof is found, they look back at all the clause selections that led to it. And the clauses that were part of that successful proof, they get a positive reward. In the paper, they used a value of 1. And the clauses that were picked but didn't actually help with the proof, those get a reward of 0. This way, the network can start to figure out, okay, these kinds of clauses are helpful, those kinds are not so helpful.
Right, so that leads us to their RL-inspired learning operator. That's the mechanism, the actual nuts and bolts of how the neural network learns from these successful proofs. And they drew on ideas from a classic RL algorithm called reinforce, and this idea of the policy gradient theorem. In essence, that theorem gives you a way to figure out how to adjust the neural network's parameters, the knobs and dials inside, so that it's more likely to choose actions to pick clauses that led to good results in the past.
And what's really cool is how they adapted this to their stateless setup. Instead of looking at these long-term rewards, they focused on those immediate retrospective rewards. So for every successful proof, they looked at all the proof contributing clauses that were available at each step, and they used those as positive examples to train the network. Then they average all those learning signals, both from the different clauses and from multiple successful proofs of the same problem. And this whole thing is iterative. You use the current network to guide the prover, collect more successful proofs, and then use those to make the network even better.
Now, onto the network itself. They call it their neural clause evaluation function. And they had two main goals in mind. First, it had to be general purpose. That means it should work well on different logical problems, regardless of the specific names used for the symbols. And second, it had to be fast, efficient enough to run inside Vampire without slowing things down too much.
To achieve that name invariance, they used a graph neural network, or GNN. It's a way for a network to understand the structure of a problem, to see how the symbols and clauses are related. And they run this GNN just once at the start of each problem to create this initial representation that doesn't depend on the specific names of the symbols.
Then they had this really clever idea to generalize to the traditional heuristics, age and weight. They used those initial embeddings from the GNN to seed two separate recursive neural networks, or RVNNs. One RVNN, it's like a supercharged version of the age heuristic. It looks at the derivation history of a clause, how it was derived from the initial axioms. The other RVNN, that's like a fancy weight function. It analyzes the structure of the clause, how it's built from symbols and variables. And to keep these RVNNs efficient, they treat those derivation and parse trees as DAGs, directed acyclic graphs. That lets them reuse computations for shared structures.
Yeah, so you've got these two specialized modules, one that understands the ancestry of a logical statement and one that understands its complexity. Pretty neat.
And to get the final score for a clause, They take the outputs from those two RVNNs and combine them with a bunch of simpler features. Stuff like the actual age and weight, the number of literals in the clause, how many variables it uses, and some information related to Vampire's avatar splitting mechanism. All of that gets fed into a small feed-forward neural network, which spits out a single score, a logit, for that clause. And that score determines where it goes in the passive clause queue. Higher score, higher priority.
They also put a lot of effort into making those RVNN computations fast. They describe this technique where they delay evaluating nodes in the trees and then process them in batches, layer by layer, based on their dependencies. This allows them to use vectorized operations, which are much more efficient. For instance, in the generalized age network, when a new clause is derived, it gets put into a buffer organized by its derivation depth. Then all the clauses at a certain depth are processed together once the parents have been evaluated. And this requires a consistent way of combining the parent embeddings and the embedding of the inference rule used to derive the new clause.
Now, for the implementation, they integrated their neural network into Vampire, specifically version 4.9. They used PyTorch for the training and then TorchScript to make it run smoothly inside Vampire, which is written in C++ better. For managing the passive clauses, they used a single priority queue, ordered by the scores from the neural network, and they added a bit of randomness, using something called gumbel noise to those scores to help the prover explore different options and not get stuck in a rut.
Right, and they also implemented this delayed insertion buffer in Vampire's passive clause handling. That way, Vampire can do its usual simplifications and check for redundancy on new clauses before they even get to the neural network. Saves a lot of computation.
The whole training process was managed by Python scripts that ran Vampire, collected data from successful proofs, used that data to update the neural network, and then repeated this whole cycle. And they used early stopping, which is a way to prevent the network from overfitting to the training data. They basically keep an eye on the performance on a separate validation set and stop training if it doesn't improve for a certain number of rounds.
For their experiments, they used the TPTP library, which is massive. They split the first-order logic problems into training and testing sets, and they gave Vampire a limited amount of computational resources for each problem. They compared their neural approach, using that single queue ordered by the network scores, to Vampire's default strategy, which is already highly optimized. And the results, well, they were impressive. After training, their system solved a lot more problems on both the training set and the unseen test set compared to the baseline.
And they looked at how much computation the neural network used. It did consume some resources, but because it made clause selection so much better, the overall performance was still way up. Plus, it needed fewer clause activations on average, which is good.
They ran some interesting additional experiments. The without imitation one was cool. They trained a network from scratch without showing it any successful runs from Vampire's default strategy. And they still saw improvement over the baseline, but the final performance wasn't as good. So there's definitely value in that initial learning from existing strategies.
Yeah, that's a great insight. Like, even if the goal is to go beyond human-designed heuristics, there's still something to be learned from them initially.
And then their boost experiment. They ran multiple trials to get more training data, and they gave more weight to problems solved in recent iterations. That's how they got their best result, that 20% improvement on the test set.
Awesome. But I think the most convincing evidence came from when they trained on the entire first-order TPTP library and gave the prover a lot more time to work on each problem. In that setting, their neurally guided Vampire solved 130 problems that had a rating of 1.0. That means no system had been able to solve them in the most recent evaluation of theorem provers. And of those, 49 were completely new solutions never seen before. I mean, that's just incredible. It really shows the potential of this approach to push the boundaries of what's possible in automated reasoning.
Absolutely. That's a huge leap forward. And there's this cactus plot in the paper which really brings it home visually. It shows a clear jump in performance for the neurally guided strategies compared to all sorts of different configurations of Vampire's default settings.
And the related work section is great. They do a good job of covering other research in this area, especially other systems that use machine learning to guide clause selection, like Enigma and similar approaches. They point out the key differences between their RL-inspired learning operator and the methods used in those other systems. One key distinction is that their approach looks at all the proof-contributing clauses at each step, not just the final ones that were selected for the proof.
Yeah, that's an important point. It's about getting a more holistic view of what leads to success.
Right. They also discuss other attempts to use reinforcement learning and various neural network architectures in theorem proving. It's really helpful to see how their work fits into the bigger picture.
So, to wrap things up, in their conclusion, they highlight their main achievements. They developed this efficient, name-invariant neural architecture that combines a GNN with two RVNNs. They came up with this RL-inspired learning operator that learns directly from successful proofs, and they achieved that remarkable 20% performance boost on TPTP, including solving previously unsolved problems. It's a real testament to the power of machine learning, especially reinforcement learning, to revolutionize a field that's been dominated by handcrafted heuristics for so long. They also point to some exciting future research directions.
Yeah, like comparing different learning operators, maybe trying transfer learning to apply these strategies to new types of problems, and exploring ways to improve the overall set of strategies used by theorem provers. It's a really fertile area for research. And as always, we'll have a link to the full paper in the show notes if you want to dig deeper.
Okay, so now for our novel notions segment, where we take the cool ideas from the paper and brainstorm some potential future directions. So here's a thought I had. Building on the neural architecture itself, what if we use meta-learning techniques to automatically design and optimize that network? Imagine a system that can look at a set of theorem-proving problems, analyze their characteristics, and then say, okay, for these kinds of problems, here's the best GNN and RVNN structure, and here are the optimal hyperparameters.
Whoa, that's a cool idea. Taking it even further, could this meta-learning system discover entirely new kinds of neural architectures, ones we haven't even thought of, architectures that are specifically tailored for the unique challenges of automated theorem proving? Maybe architectures that are really good at spotting certain logical patterns or relationships that our current models miss.
Exactly. It would be a marriage of neural architecture search and reinforcement learning for theorem proving. And the obvious advantage is that different types of logical problems probably have different underlying structures, right? So they might need different neural networks. But the really exciting part is that this meta-learner might stumble upon some truly novel, incredibly effective network designs. Designs that could lead to even bigger breakthroughs in ATP. Designs that go beyond what we as humans have typically focused on.
That's a really intriguing direction. So what kind of real-world impact could we see from something like that?
Well, ultimately, it could lead to this new generation of automated theorem provers. Provers that are not just more powerful, but also way more adaptable. They could tackle a much broader range of logical problems with greater efficiency. And maybe, on a deeper level, the process of meta-learning these architectures could give us a whole new understanding of what makes for good theorem proving strategies.
I love that. My own thought is, we've seen these incredible advances in natural language processing, right? Like, what if we could use NLP techniques to extract meaning, not just from the logical structure of the problems, but also from the descriptions and comments that are often included in problem libraries like TPTP? Could that kind of semantic understanding guide the clause selection process even further?
That's a fantastic question. Imagine a neural network that's enhanced with NLP capabilities. It could actually understand the high-level concepts and goals described in the problem statement. And then it could use that understanding to prioritize clauses that are semantically relevant to reaching those goals, even if those clauses don't seem promising based just on their logical form or their derivation history.
So it'd be like the prover has this intuition about what the problem is really asking, not just the raw symbols.
Yeah, exactly. It would be this fusion of language understanding and neural theorem proving. I mean, we already know that problem names and descriptions can give us hints about the underlying mathematical ideas or the intended solution strategy. But what if the network could learn to spot these subtle semantic connections between the problem statement and the logical clauses? Connections that a purely syntactic analysis would totally miss. That could be super helpful for problems that deal with abstract mathematical concepts or require a deeper understanding of the specific domain.
It seems like this whole intersection of machine learning and automated theorem proving is ripe for innovation. These self-learning provers are pushing the boundaries of what we thought was possible.
Totally agree. It's an exciting time to be working in this area.
Well, that wraps up our deep dive into efficient neural clause selection reinforcement. We hope you enjoyed this exploration of this really cool area of research. And as you think about all this, here's something to ponder. As AI systems become increasingly capable of learning these complex strategies in domains like theorem proving, what other fields that currently rely on human intuition and expertise could be transformed in a similar way? by letting the machines learn directly from experience what new possibilities might open up. Thanks for listening to TalkTensors, and we'll catch you next time for another deep dive into the world of machine learning research.